In this class, we are going to discuss time-dependent perturbation theory. So far, we have been considering Hamiltonians that do not depend explicitly on time. In nature, most quantum phenomena are governed by time-dependent Hamiltonians. Time-dependent perturbation theory is most useful for studying processes of absorption and emission of radiation by atoms, or more generally for treating the transition of quantum systems from one energy level to another. So we are actually dealing with the time-dependent Hamiltonians in time-dependent perturbation theory, and in this case this Hamiltonian is capable of splitting into two parts, a time independent part which is h0 and the time dependent part. So let me put it by w. So w of t. So this is the time dependent part of the Hamiltonian, while h0 is time independent. So H0 here basically describes the system when unperturbed, and it is assumed to have exact solutions that are known. So in this lecture I will be using the capital letter psi like this to represent the time dependent state vectors, and I will use a small uh, psi to represent the time independent part of the state vectors. So the time dependent Schrodinger equation of systems. So we had learned the time dependent Schrodinger equations. So if you remember, it is given by I h cross dou by dou t psi of t is equal to h into psi of t. So this is going to be this is the time dependent Schrodinger equation, where this capital psi represents the time dependent state vectors h psi of t, and h of course is a time dependent Hamiltonian as given by this equation 1. Now the time dependent Schrodinger equation of systems whose Hamiltonian is independent of time is separable into a spatial and time coordinates. So we can actually write this psi n of t, this psi of t, or in general you can write the psi n of t as e raised to minus I e n t by h cross small psi n. So this is possible if the Hamiltonian is independent of time, and then you can write this psi n of t as the product of two parts, one time dependent part and then time independent part, and the eigenvalues of this time dependent part will give us e raised to minus I n t by h cross, and this small psi n represents the time independent part, where this small psi n also satisfy the time independent Schrodinger equation. This one satisfy independent Schrodinger equation. What is that? We have h0 psi n equal to en psi n. So here this h0 is time independent Hamiltonian. Okay, usually we put some superscript 0 over this psi n to say you that the Hamiltonian is independent of time in this case. So this is only if the Hamiltonian is independent of time, but the state vectors are time dependent. Then you will write a psi n 0. So this superscript 0 represents this part, or the superscript 0 indicates the case that the Hamiltonian is independent of time. Now we assume that in the time interval, let's consider some time interval, let's say t prime, between some limit 0 and t. In this time interval, we subject the system to an external time dependent perturbation that is given by W of t. W is of course it's a time dependent perturbation part of the Hamiltonian, it's an operator, and we assume that this is a very small perturbation compared to the non-perturbed or the H0 part of the Hamiltonian. So you can write W of t is equal to W of t in the time interval 0 to t. Then it is 0 all other limit of this time slot for time less than 0 or greater than t. If you plot this perturbed Hamiltonian as a function of time, you can see that this perturbation happens only for a particular time interval between 0 to t. Okay, so in all other regions it is 0. So that means the perturbation is a time dependent perturbation, and it happens only during this particular time interval. So during this time interval, the Hamiltonian of the system then of course will be given by H0 plus W of t. Now with this Hamiltonian, the Schrodinger equation can be written as IH cross dψ by dt equal to x0 plus W of t into psi of t. So let's say this is our equation number 4 and this is equation 5. This W of t, it basically characterizes the interaction of the system with the external source of perturbation. Now the effect of this W of t is that when the system interacts with this external perturbation, it either absorbs or emits energy. So this causes the system to undergo transitions from one unperturbed eigenstate to another. So the main part of time dependent perturbation theory consists of answering this particular question. Let's say suppose we have the many eigenstates. Let me draw some eigenstates here, some arbitrary eigenstate. Suppose these are the eigenstates of the unperturbed Hamiltonian H0. Now at some particular instant, let's say our system is in an initial state given by this psi I. Now if the system is initially in this unperturbed eigenstate psi I of H0, then the main task of time dependent perturbation theory consists of answering the question, what is the probability that the system will be found at a later time in another unperturbed eigenstate psi f. See what I was telling you, your system was initially in this state before you switch on the perturbation. So this actually corresponds to one of the eigenstates of unperturbed Hamiltonian. Now you have switched on the perturbation for a particular time interval. Then after that you again switched off the perturbation, but the system, due to this interaction of the perturbed Hamiltonian, the system might absorb energy or it might emit some energy, and it might have made a transition to a final state psi f. And what we are going to do in time dependent perturbation theory is to find out the probability of being found the system in this final state, and this state is also one of the state corresponding to unperturbed Hamiltonian, and this psi f can be above this psi I or it can be below also. So if the energy absorption happens, psi f can be above this initial state, or if emission is happening, it can be below this initial state. So we are going to find out this probability, or that's what we basically do in time dependent perturbation theory. For this, we have to look for solutions of the Schrodinger equation given by this equation 5. For this, the standard method is to expand this psi of t in terms of some expansion coefficients Cn of t. So what we do is we expand this time dependent state vector capital psi of t in terms of, let me write it, sigma n psi n 0 psi of t, and this is equal to this can be written as summation over n Cn of t psi n 0 of t. See, what I did is actually I expanded these state vectors of time dependent perturbation in terms of the state vectors of unperturbed Hamiltonian. So this capital psi n 0, these are the state for the unperturbed Hamiltonian. Of course, those are time dependent states, so that's why I have written it in capital letter psi n, and this superscript 0 tells you that those are for the unperturbed Hamiltonian. So that means, so this will be the state when your perturbation is 0, or when you don't have any perturbation in the system. Okay, so this inner product psi n of t into psi of t is given by this expansion coefficient Cn of t. Of course, it's a time dependent function. Now, from the previous equation, this one, equation number 2, you can see that these state vectors of unperturbed Hamiltonian psi n 0 of t can be written like this: e raised to minus int by h cross into small psi n, the time independent part of the wave function. So let me write this equation as this is equal to summation over n Cn of t, the expansion coefficient, e raised to minus ient by h cross small psi n. Let's say equation 6. Now what we do is, so we substitute the psi of t in our equation 5 in order to solve this. So this is what we have to basically solve to study the time dependent perturbation theory. Okay, so we substitute for psi of t in equation 5, and let's see what we get. On left hand side we will be having I h cross d by dt, and then for capital psi n of t we put it as summation over n Cn of t small psi n e raised to minus ient by h cross, and this is equal to, on right hand side we have h0 plus the perturbed part of the Hamiltonian, or the time dependent part of the Hamiltonian, summation over n Cn of t small psi n e raised to minus ient by h cross. That is I h cross summation over n. You can take this differential inside, you have to differentiate the entire terms. So this will be d by dt of Cn of t, then psi n e raised to minus IE and t by h cross plus I h cross summation over n Cn of t, then d by dt of small psi n e raised to minus IE and t by h cross plus, if you differentiate the third term, what you get is plus IH cross summation over n Cn of t small psi n, then we have e raised to minus IE n t by h cross, then the differential of e raised to minus I n t by h cross will give us one more term minus IE n by h cross, and on right hand side what we have is summation over n Cn of t. If you split that Hamiltonian, we will be having h0 psi n e raised to minus IE n t by h cross plus summation over n Cn of t w of t small psi n e raised to minus IE n t by h cross. Now we can simplify this expression, and the first simplification is that, as you know, the time derivative of this term will be 0 because this small psi n is time independent function. So all these second term will vanish from this expression, and from the right hand side, if you know this h0 into psi n should give us en into small psi n, and on left hand side you have this this I into minus I, so this will give us a positive real quantity. Then this h cross and h cross can be cancelled, so what you get basically here is same this term. So you can see that this one and this one, they cancels, these two cancels, both are same. So the remaining terms can be written as, on left side we have IH cross summation over n d by dt of Cn of t, then small psi n e raised to minus IE n t by h cross, and on right hand side we have summation over n Cn of t w of t small psi n e raised to minus IE n t by h cross. So we got a much simpler expression, and now we are going to multiply the entire expression by some state vectors, some arbitrary bra vectors, let's say psi m. So if you multiply this entire expression by psi m, we can write it as IH cross summation over n d by dt of Cn of t, then you have psi m psi n e raised to minus IE n t by h cross equal to, on right hand side, summation over n Cn of t, then you have psi m w of t psi n, then e raised to minus IENT by H cross. Now you can see that this inner product psi m psi n is a delta function. This is delta mn. So out of all the summation of n, only one time survives. That happens when this n equal to m. So the surviving time that you get out of this all the summation is cm time. And this is the matrix elements w of mn. It's a time dependent function. It's a matrix element wmn. So this can be simplified as IH cross. Now you don't have the summation, you have only one surviving time, so that is given by Cm of t instead of Cn, Cm of t, then e raised to minus I E M t. Here also only one time survive. That's when En equal to Em. E raised to minus IEMT by H cross is equal to summation over n Cn of t W mn, the matrix element, e raised to minus IENT by H cross, or you can write IH cross d by dt of Cm of t equal to summation over n Cn of t matrix element Wmn. Then you can take that energy time to the right side, so that will become e raised to plus I mt by h cross. So that can be written as e raised to I em minus en into t by h cross. So this can be written as summation over n Cn of t Wmn, the matrix elements, then e raised to I omega mn t by h cross, where the omega mn is given by these expressions e raised to em minus, see all this quantity, em minus en by h cross gives us the omega mn. So we put some equation number, let's say equation 7, and this is an exact equation, and so far we haven't used any approximation techniques. Okay, so this is the equation which we want to solve, and so we will be using the perturbation theory to proceed further. Let's first consider the first order perturbation. So in this case, we assume that, or we write this time dependent potential as lambda into W prime. Okay, so this lambda is a dimensionless parameter, and it has the same meaning like what we did, like what I said during the discussion of time independent perturbation theory. So it is a dimensionless parameter, and it can have values from 0 to 1, and 0 means it's a completely unperturbed system, there is no perturbation at all, and when lambda equal to 1 means there is a complete perturbation. But we have also discussed that lambda should be much less than 1 for the approximation techniques to be valid, or in order to converge the expansion series. Okay, so we make this assumption that W of t is lambda into W of prime as in time independent perturbation theory, and we express the coefficient Cn of t in the power series of lambda. So you can write Cn of t as Cn0 of t plus lambda Cn1 of t plus lambda square Cn2 of t plus etc. So to converge this series, this condition has to be satisfied. Lambda should be very less than 1. Then you need to consider first few terms in the expansion. So if you substitute this back in our equation 7, which we have just developed, we can write equation 7 as IH cross, then we have d by dt of this entire expansion terms. So this will be d by dt of Cm of 0 plus lambda d by dt of Cm of 1 plus lambda square d by dt of Cm of 2. All these are time dependent function. I just avoided the explicit writing of time dependency just to appear it in a simple way. So these are time dependent functions plus etc. On right hand side we have equal to summation over n lambda w prime mn matrix elements. Then we have Cn of 0 plus lambda Cn of 1 plus lambda square Cn of 2 plus etc. into e raised to I omega mn t. So now we equate the coefficients of various powers of lambda on either sides of this equation, like what we did in the case of time independent perturbation theory. If you equate the coefficients of lambda raised to 0, that means the terms without any lambda, then from left hand side you have IH cross d by dt of Cm0, and there is no such terms on right hand side, so this will be 0. So it tells you that d by dt of Cm of t is equal to 0, or what we have is Cm of 0 is a constant. Okay, so this is the unperturbed case of the system. So it remains like a stationary state. There is no change in the expansion coefficient value Cm or Cn as it remains constant in the zeroth order approximation. Now to get the first order correction, we equate the coefficients of lambda raised to 1. So if you equate the coefficients of lambda raised to 1 from both sides, you can see that on left hand side we have IH cross d by dt of Cm0, and on the right hand side we have, when this term multiplied by this one, there is a lambda term here, so that will give us a lambda raised to 1 term. So this can be written as Cn of 0, of course there is a summation over n, Cn of 0, the matrix element the w prime mn, it's a function of time, e raised to I omega mn t. So let's say this one is our equation 10 and this is equation 11. Now if you look back what this Cn of t was, let me say this Cn of t was actually an expansion coefficient psi n0 psi of t. Okay, now psi n of 0 is the eigenfunction of h0, and this one represents some initial state of the system. So this eigenstate, we have seen that it can be further written as e raised to minus IENT by h cross in small psi n if this Hamiltonian is time independent. So h0 is time independent. So what we have is this is equal to Cn of t is equal to e raised to IENT by h cross. Then you have small psi n, then capital psi of t. So this is the expansion coefficient Cn of t. So if initially the system is in some state, let's say some state psi L, some state, then what this term represents is psi L. So psi of t is the time dependent. It gives you the state vectors at different times. Okay. So if initially you assume that your system is, if you remember the eigenvalue spectrum that I have drawn before, so you have an eigenvalue spectrum of unperturbed or time independent Hamiltonian H0, and what we assume is that initially this state psi of t is given by any one of these possible eigenstates. Okay, so that state we assume as psi L. Let's say you have a state psi L. So initially you say that your system is in this particular state, and then you switch on the perturbation. Then something happened. The system, suppose if it has absorbed some energy, then it make a transition to a higher state. So we are going to, so what we were trying to do is we were trying to get or an expression for the probability for this transition. Okay, so what I was telling is, you can assume that this initial state of the system is given by one of the possible eigenstates of the unperturbed Hamiltonian, right? In that case, your Cn of t will become e raised to IENT by h cross. Then you have psi n, then you have psi l. So what you get from here is e raised to minus e raised to IENT by h cross. Then you have a delta function here, delta nl. Okay, so let's say this is Cn of 0 when time t is equal to 0, and we assume that at time t is equal to 0 the psi of t is given by this initial state of the system psi L. Then you can write Cn of 0 is e raised to IENT by h cross delta nl. So given the initial state, we know the value of Cn0, the expansion coefficient of the initial state, in terms of the eigenbasis of h0, and we use this Cn0 to solve for the higher order terms of these expansion coefficients like Cm1, Cm2, etc. So if the initial state of the system is in psi L, like what I told here, Cn0 is given by this delta function, delta nl. That means the probability is 1 in the state psi L, and the probability for finding the system in any other state other than this psi L is 0. Now, after the introduction of time dependent perturbation, as I mentioned before, our aim is to find what is the probability that the system is found in a state, let's say psi m, at time t. So let's say this is our state psi m. Okay, so initially we had this state psi L, and then we are looking for what is the probability of finding the same system in another unperturbed state of the Hamiltonian psi m. All these states are the states of unperturbed Hamiltonian, so that you should keep in mind. See, we are not making any change in the energy spectrum or the eigenvalue spectrum of the uh, particular system. The only thing is that as a consequence of the time dependent perturbation, system make a transition. It can be either to an higher energy level or it can be a lower energy level. So this psi m state in principle can be above or below this psi L state, and if it is above, this is usually when it absorbs some energy, and this psi M state can be below this initial state when the system emits some energy or when some emission is happening. Okay, so we are going to write then d by dt of Cm of 1. I made a mistake while writing this equation 11. When you equate the coefficients of lambda raised to 1, on left hand side what we have is Cm raised to 1, not Cm0. So this must be Cm1. So please correct this in equation 11. The left hand side is Cm raised to 1, not Cm0. So you can write d by dt of Cm raised to 1 is equal to, if you take the IH cross to the right side, IH cross summation over n, then we have this delta NL function, then e raised to I omega m n t psi m. So let's explicitly write down the matrix elements of the perturbed Hamiltonian. So that will give us psi m w prime psi n. This is 1 by IH cross. So out of these many possible values for n, only surviving term is n equal to L. So this will be e raised to I omega m L t psi m w prime psi L. So to get this expansion coefficient, Cm of 1 into t is equal to 1 by IH cross. Then you have to integrate the right side between the limit 0 to t, or during the duration in which you have switched on the perturbation. So this is e raised to I omega m L t prime psi m w prime psi L dt prime. Now this is the expansion coefficient Cm1. So this expansion coefficient can be interpreted as the probability amplitude of finding the system in state m at time t. So that means the probability for the transition, you can write the probability for transition from a state L to a state M can be written as, so we write it as P L to M, capital P L to M, and this probability is a time dependent function. So this is the square of this probability amplitude, the expansion coefficient. So this can be written as the modulus square of 1 by IH cross integral 0 to t e raised to I omega m L t prime, and you have psi m w prime psi L dt prime square. Usually we write this as this, instead of L we take some initial state I, and instead of M this takes some we consider it as the final state of the transition. So we can make the probability density for making the transition from some initial state to the final state as a time dependent function, then this is given by 1 by I h cross integral 0 to t e raised to I omega m l t prime. Then you take the psi f, the final state, then this omega fi t prime psi f w prime psi I, the initial state, dt prime whole square, the modulus square of all these quantities. So this is an important expression for us, and this one tells us what is the probability for the system to make a transition from some initial state psi I, we take it as now psi I, to some final state psi f. So this probability for an optical absorption or an optical emission or an energy absorption or energy emission in general is given by this particular expression. So we will be using this expression to solve some problems later. Most of the selection rules in spectroscopy is obtained from this equation. So for a finite probability for transitions from some initial state to the final state f2 takes place, we must have a non-zero value for the matrix element. So most of these selection rules are actually determined by this condition that a non-zero matrix elements are required to get a finite probability. So this is very important for us. So this must be not equal to 0 for getting a finite probability. And if you impose these conditions, and if you know the nature of the perturbation Hamiltonian, then you can get the selection rules in spectroscopy. So now let's quickly see the second order equation or the second order correction. So for this, what you have to do is you have to go back the expression in the expansion equation 9. If you equate the coefficients with the lambda square on both sides, so here you have a cm lambda square d by dt cm of 2 on the left hand side, and on right hand side when you multiply this lambda with this lambda, we will be having a term of lambda square. So if you equate such coefficients, we get a second order equation I h cross d by dt of cm2 equal to, on right hand side we have cn1 e raised to I omega m and t psi m w prime of t psi n. So this is the second order equation. So we know that how to get cn1, because cn0 we assume some initial state, and from that we can calculate expressions like cn1, and then if you put those things here you can calculate cm2. In general you can see that you can do this in an iterative manner, so any higher order correction terms can be obtained, like I h cross d by dt of cm of r can be any higher order terms, summation over n cn of r minus 1 of t e raised to I omega m n t psi m w prime of t psi n.